going to take a class on 18 electron rule. 18 electron rule is used to predict the structure and stability of organometallic complexes. In the 18 electron rule, ligands are considered as Lewis bases which donate the electron to the metal atom, and the metal ion will act as Lewis acids. When the metal atom or ion achieves an outer shell configuration of Ns2, N-1, D10, Np6, there will be 18 electrons in valence orbitals, and this corresponds to a stable configuration. There are various applications for 18 electron rule. It can predict the stabilities and structures of organometallic compounds, it can predict the number of metal-metal bonds, and it can predict whether the ligands will be bridging or terminal. In order to understand the 18 electron rule, we can make use of the molecular orbital diagram for a complex of octahedral symmetry. For an octahedral complex, the most stable arrangement is the one in which the bonding molecular orbitals are completely filled and all the anti-bonding molecular orbitals are empty. In the case of octahedral complex, the A1G, T1U, EG and T2G orbitals are the bonding molecular orbitals. And in order to fill these 9 orbitals, we need 18 electrons. And hence, we get the 18 electron rule. The complexes in which the crystal field splitting delta O is large. This corresponds to the stable configuration. And in such systems, if you try to put an extra electron into the Eg star orbital, the system will become unfavorable. And hence, in such systems, always they will obey the 18 electron rule. For example, you can take the case of carbonyl or nitrosyl complex. The speciality of the carbonyl or nitrosyl complex is that they contain the ligands which are able to stabilize the T2G orbital. And as a result, the crystal field splitting will be large. And generally, such complexes will obey the 18 electron rule. At the same time, if you look onto the complex in which the crystal field splitting is low, that is the delta O is low. For example, like halides, what happens is that the Eg star orbital will be filled with the electrons. And in such system, the 18 electron rule will not be obeyed because the delta O is small and hence the electrons can fill onto the Eg star orbital. And hence such systems will deviate from the 18 electron rule and they may contain more than 18 electrons. Two methods are available for the electron counting in the 18 electron rule. The first one is the neutral atom method or covalent method. The second one is the oxidation state method or ionic method. This table shows the number of electrons donated by various ligands in the neutral atom method and oxidation state method. In the oxidation state method, along with the electron contribution, we should have a knowledge about the formal charge of the ligand. Then only we can apply the oxidation state method. Here we can see that if we take a neutral ligand, the number of electrons donated by that particular ligand in the neutral atom method and the oxidation method is same. At the same time, if you are taking an anionic ligand or cationic ligand, the number of electrons donated by the ligand is different. And here we will move on to some examples, and here we can see how to apply the neutral atom method. So in the first case, I have taken a hexacarbonyl chromium complex, and we know that this is a neutral complex and the oxidation state of chromium is 0. Each chromium can donate 6 electrons and each carbonyl can donate 2 electrons. There are 6 carbonyl and hence the total will be 12 electrons. And if you take the sum, you will get 18 electrons. It means that this complex obeys the 18 electron rule and hence this is stable. Next we can take the case of a phosphine complex. Here this is a nickel based phosphine complex. Here the nickel can donate 10 electrons and the phosphine can donate 2 electrons. The phosphine is also a neutral ligand and hence the nickel will not have any charge. And when you take the sum, you can see that it is 18 electrons. And next one is a mixed complex which contains both carbonyl as well as the phosphine ligand. We know that both of these ligands are neutral and hence the oxidation state of ion will be 0. The ion can donate 8 electrons, each carbonyl can donate 2 electrons and hence 4 carbonyl, the total sum will be 8 electrons. and the phosphate can donate 2 electrons, and the total sum is 18 electrons. And hence we can say that all these three complexes obey the 18 electron rule, and hence they are stable. We can see a few more examples. This is a manganese-based complex. In the manganese-based complex, you can see that the manganese donates 7 electrons, and the 5 carbonyl will donate 2 electrons each, and hence the total electron count of the pentacarbonyl manganese compound is 17 electrons. Based on this, we can say that this does not obey the 18 electron rule, and hence this should be unstable. The experimental evidence also show that it is difficult to isolate this compound because it is unstable. Similarly, a cobalt complex, that is a tetracarbonyl cobalt complex. Here the cobalt donates 9 electrons and the carbonyl donate 2 electrons each. Again, the total electron count is 17 electrons. And hence, this complex is also unstable because it does not obey the 18 electron rule. At the same time, if we try to take the corresponding anion of the manganese complex or the cobalt complex, we can see that they obey the 18 electron rule. Let's see how we have to take the total electron count. The manganese, it donates 7 electrons, carbonyl, it donates 2 electrons each, and we have an extra charge. So it's a negative charge, so we have to add 1 electron. If it is a positive charge, we have to minus 1 electron from the total electron count, and we get a total electron count as 18 electrons. Similar is the case of the cobalt-based complex. Okay. So here we can see that these anionic complexes are stable with relative to the neutral complex. And the another one is a dimer complex, that is Mn2CO10 times. This is a stable complex. We can see that here there are 2 manganese atoms, and each manganese will donate 7 electrons each, and it will be 14 electrons. And each carbonyl donate 2 electrons each, and there are 10 carbonyl, so 20 electrons. And apart from this, it has a metal-metal bond, and each metal-metal bond donate 2 electrons to the total electron count. Here the Mn-Mn bond, it is a single bond, so only 2 electrons. And here we can see that the total electron count is 36 electrons, which means that 18 electrons per manganese, and hence this complex is stable. Experimentally also, this is a stable complex. Similarly, we can apply it to the cobalt-based complex. Let's see what is the difference between the neutral atom method and oxidation state method. So here we have taken an example of a manganese-based complex HMnCO5 times. So in the neutral atom method, the manganese is a 7 electron donor. The 5 carbonyls will donate 10 electrons, and the hydrogen, it will donate 1 electron, and the total electron count is 18 electrons. And in the oxidation state, first of all we have to assign the charge of the ligands, and we have to find out the oxidation state of the metal. Here the metal is present in the +1 oxidation state. Correspondingly, there will be only 6 electrons present on the Mn+. The 5 carbonyl, it will donate the 10 electrons, and here the hydrogen, it is present as a hydrate ion, and hence it can act as a 2 electron donor. So if you take the total electron count, here also we get 18 electrons. So irrespective of the method, the total electron count of the system will be same. So it is our interest which one to use. We can use either the neutral atom method or oxidation state method. But if we want to apply the oxidation state method, we should know the charge of the corresponding ligands. Now let's apply the neutral atom method and oxidation state method to a rhodium-based compound. Here there are 2 rhodium atoms. Each rhodium will donate 9 electrons each, and the total electron count will be 18 electrons. The 4 terminal carbonyls will donate 2 electrons each, and there are 2 chlorine atoms which are in the bridging position. Each bridging carbonyl can donate 3 electrons, and hence the total electron count is 32 electrons, which means that 16 electrons per rhodium atom. We can see here that it does not obey the 18 electron rule, but there are certain compounds which does not obey 18 electron rule. Instead of that, they will obey the 16 electron rule. Okay. The 16 electron rule is applicable to the square planar complexes. So this will come under that category. Now let's look on to the oxidation state method. In the oxidation state method, first of all we have to assign the charge of the ligands. So here carbon is a neutral ligand, whereas the chlorine, it is having a negative charge. And as a result, the rhodium, it exists as a cation. Each rhodium atom Instead of rhodium atom, we are having a rhodium ion. As a result, each rhodium ion it is a 8 electron donor, and hence you will have 16 electron. And the carbonyl, it will just donate the 2 electron as same. And now the chlorine. When it is existing as a bridging ligand, in the oxidation state method, it will act as a 4 electron donor. And hence the total electron count is again 32. So as I have already mentioned, whichever method you use, you will get the total electron count to be the same. And here is the last example, which is a tungsten based compound. Here we can see that in the nuclear atom method, the tungsten is a 6 electron donor. There are 2 carbonyls, each act as a 2 electron donor. And here there are 2 types of cyclopentadiene rings. One is a eta 5 cyclopentadiene and another one is a eta 3 cyclopentadiene. The eta 3 cyclopentadiene, it is a 3 electron donor, and eta 5 cyclopentadiene is a 5 electron donor. And correspondingly, this complex will be the 18 electron donor. And in the oxidation state method, we have to assign the charge of the ligands. The cyclopentadiene is actually acting as an anion. Both eta 3 cyclopentadiene as well as eta 5 cyclopentadiene, they will act as anion. Correspondingly, the tungsten will be having a charge. The tungsten 2 plus, it will act as a 4 electron donor. The carbonyl, it's a 2 electron donor. And the eta 3 cyclopentadiene anion, it is a 4 electron donor. And eta 5 cyclopentadiene anion, it is a 6 electron donor. And we got it as a 18 electron. So again, here I am repeating the same thing. Whichever method you use, you should get the same total electron.